Okay, good afternoon. We are here, and it's a pleasure to be here with Professor Robert Pindyck. And I would like to present his seminar. The seminar is a seminar that is inside a group of seminars that is economic modeling seminars. That is a seminar that is composed by the seminar of Robert Pindyck. After that, we should have Jeffrey Hill, after the Professor Zwart, and finally Bergman for February 2021. This is a series of economic modeling seminars that was arranged by Italian Association of Environmental Resource Economists, University of Brescia, Fondazione Enrico Mattei, and the collaboration of European University Institute, Università di Siena, and the Department of Environmental Science and Policy of University of Milan. First of all, I would like to present Professor Pindyck, that is a professor of Bank of Tokyo Mitsubishi Professor in Finance and Economics and Professor of Applied Economics at MIT Sloan School of Management. His research is on many different topics. The first is the economics of catastrophes, that is exactly the topic of today. Environmental economics and public policy, energy and commodity markets, macroeconomics, regulation, antitrust, natural resource markets, in the investment under uncertainty. The research of Professor Pindyck is very, very long. There is a long list of papers. Among them, we have the most important papers review in the world according to economics. That is American Economic Review. There are 7 papers, Quarterly Journal of Economics, 3 papers, Journal of Economic Literature, 5, Review of Economic Statistics, 5, and others. The list is very, very long. We have 100 of papers in which we have a Journal of Economic Dynamics and Control, Energy Economics, Energy Journal, GIM, and others that are very important for us. So we are at the top ranking of the research papers. Among the books of Robert Pindyck, we have Economic Model and Economic Forecast, Macroeconomics. Both are written with Rubenfield and are very famous in the world, also in Italy. And the last one is Investment Under Uncertainty. This is one of the classic book on a real option approach. It is one of the most important. It's also, I think, the first one in which they started to speak about a real option. Robert Pindyck, according to the international ranking of the most influential authors, that is this largest bibliography database dedicated to economists, Robert Pindyck ranks among the top environmental economists, energy economics, and resource economics. But in my mind, this is amazing. I think it was the most impressive result is that the influence of Robert Pindyck in economics and all these topics. In the long list of curriculum of Robert Pindyck, we have also honors and awards. I have taken only some of them in order to give the idea about the Excellence in Teaching Award, a prize, an award for papers, and also the Jamison Prize of Excellence in Teaching 2018, that is the last one. And also consulting, very long, and private and public. Public, we have a Federal Reserve, World Bank, U.S. Department of Energy, and then consulting among the last one. I've taken only the last in terms of we have a Verizon, Medtronic, Air Mexico, and Compaq, and many others. So in my mind, I think is an honor to have here Robert Pindyck, and I think it's the best manner in order to start with our list of presentation and seminars, also because I think is the highest, one of the highest researcher and teacher in the world in economics. So I leave the floor to Robert. Thank you for being here, and thank you to everybody.
Okay. Thank you, Sergio. That was a very generous introduction. I wish I could be in Italy right now, because then after the seminar we'd go out and have a wonderful dinner. But this will have to do. So thank you everyone for being here and listening to this. Let me, first of all, I assume all of you can see the screen, the slides that I'm going to show. This is
Yes.
joint work with Ian Martin from LSE, welfare costs of catastrophes, lost consumption, lost lives. Let me give you some background. So this builds on our earlier work, Averting Catastrophe, the Strange Economics of Scylla and Charybdis, that came out in the American Economic Review about 5 years ago. And just to briefly summarize what that work was about, the idea is that we as a society face multiple potential catastrophes. They haven't happened, all of them, but they could. Nuclear terrorism, bioterrorism, major pandemics, climate change. Which ones of these should we avert? And if we do simple cost-benefit analysis, and for each one, the benefit exceeds the cost, should we avert them all? And we show that you shouldn't. And what we do is using willingness to pay, WTP, willingness to pay as the measure of the benefit of avoiding a catastrophe, and a permanent tax on consumption, TAU, to measure the cost. We show if you have capital N types of catastrophes that are independent, we show which ones to avert. And that's the main result in that earlier paper, a rule for determining the set of catastrophes that should be averted. Now, there's a problem, and that is that work is based on a loss of consumption. If you avert a catastrophe, you avert a loss of consumption. And in fact, all of the literature on consumption disasters, I'm sure many of you are familiar with that literature, is based on a loss of consumption. But for many catastrophes, it's death that happens, not just consumption. People die, and of course that's the case now with COVID, with the pandemic we're in. So this was a big shortcoming of the earlier work. We didn't treat death, and that's what we're going to do here. Before I go on, I just want to show you a diagram, two diagrams from the earlier paper. And this shows for 7 different catastrophes, potential catastrophes, which ones to avert and which ones not to avert. This is a 45-degree line where benefits just equal cost. Anything above the line, the benefits exceed the cost. But it turns out that if the coefficient of social risk aversion is 2, there are only 5 that we should avert and 2 we should not, including climate. I want to point out that the biggest benefit for averting a catastrophe is a virus, a pandemic. And we wrote this paper, it was published 5 years ago, and we said then, watch out, a pandemic is the most serious potential catastrophe. And here it is, if the coefficient of risk aversion is equal to 4, if we raise it, now we should indeed avert a climate catastrophe, nuclear terrorism, floods and storms, but not earthquakes, bioterrorism and storms, earthquakes, and bioterrorism. Okay, here's the framework for what we're doing now. We have identical consumers. So we're not worried about people of different age groups or people who have different incomes. We're going to assume that everybody's the same. Capital N consumers, each one consumes a quantity, capital C, all right? And if there were no catastrophes, C, consumption, this is per capita consumption, would grow at a rate G. And the population, N, would grow at a rate little n. And we can normalize these so that initially consumption and population are equal to 1, okay? And there are 2 kinds of catastrophes that could happen. A consumption catastrophe in which consumption falls by a fraction phi, which is random. So it falls by a random fraction, and that catastrophe arrives as a Poisson arrival with an arrival rate lambda c. The second kind is what we call a death catastrophe, and here the population falls by a random fraction psi. The arrival rate is lambda d. And if a death catastrophe occurs, we assume that the consumption of those people remaining alive doesn't change. And by the way, that was the case during the Spanish flu, the great pandemic of 1918. A lot of people died, but the consumption of those who remained alive was largely unchanged. Now here, it's just a death catastrophe. Of course, we're going to talk about pandemics because that's what's the most relevant death catastrophe right now. But right now, it's just a death catastrophe. And we want the willingness to pay to avert each one, to avert a consumption catastrophe, to avert a death catastrophe, and to avert both. What would society be willing to give up? What is the social reservation price to avert these catastrophes? That's what we're looking for, okay? So here is the framework. We need a welfare framework. A living person gets a utility based on consumption, U of C. And a person who dies gets a utility, V of C, which for now is completely general. Now you might ask, wait a minute, somebody who's dead gets utility? And the answer is absolutely. In fact, the entire VSL, value of a statistical life, literature is based on two contrasting welfares, the welfare of those alive and the welfare when you're dead. Now, why should you have any utility when you're dead? Why isn't V 0? Well, first of all, people make bequests, which depend on income and thus consumption. So it may be that when you die, your children or grandchildren or favorite charities or whatever will get a bequest. And then governments redistribute wealth. They tax wealth and redistribute it at death. So this means that the utility, the social utility of a person who dies is not 0. Now, N is the number of people who are alive, and N star is the number if there were no deaths. We use an asterisk, a star, to denote no catastrophes. So if there were no catastrophes, no deaths, then N star minus N would be the number of people who have died, all right? The number who would be there if there were no deaths minus the number alive. The difference is the number who have died. Well, what is total welfare? Total welfare is the expected value of the number of people who are alive times their utility based on consumption, discounted, plus the expected value of the number who have died times their utility, discounted, all right? And by the way, if you don't like, some people immediately say, what do you mean there's a utility when you're dead? You get utility. The entire literature on value of a life, on the value of health, all of it is based on utility when you're dead. So if you don't like this, you have to get used to it because it's everywhere in the literature on the value of life. Okay, we make a key assumption, and I have to tell you now, without this assumption, everything becomes very complicated. The math, everything is complicated. With this assumption, everything is easy. We're going to maintain this consumption utility, this assumption that utility is constant relative risk aversion. Here's the utility function. Okay, c to the 1 minus eta divided by 1 minus eta. Eta is the coefficient of relative risk aversion, and we're going to assume it's greater than 1. And indeed, the entire literature in finance, macroeconomics, puts eta at around somewhere between 1.5 and 5. So we're going to assume it's greater than 1. Okay. Now, what's the welfare loss for a person who dies? Before we simply said it's V, but we didn't say what V of C is. So what happens when you die? All right. So there are 3 ways to handle this, 3 approaches that people use. One approach is that when you die, your consumption goes to 0. You stop consuming. The problem with that is that with constant relative risk aversion and a coefficient of risk aversion greater than 1, utility goes to minus infinity as C goes to 0, and we can't handle infinities. So that's no good. Another approach is what's called critical level utilitarianism. Utility goes to a consumption level based on, we call it CM, a minimal consumption just enough to sustain life, all right? But how do you figure out what that is? What consumption would it take to sustain life? That's tough. And besides, we want to allow for the possibility that consumption falls below that. So we're not going to use that. By the way, philosophers like this, they use this quite a bit. Another approach is the loss is foregone utility. In other words, when you were alive, you had some utility. When you die, you lose that utility. And this is used frequently, but it underestimates the loss. And let me show you why. Suppose risk aversion, the coefficient of risk aversion is 2, and consumption is 1. That means utility is -1. All right. So what is the welfare change if you die? Is it just the loss of this utility? In other words, -1, or is it something bigger? Well, suppose that consumption falls by 75%. It falls from 1 to 0.25. That means your utility moves to -4. And what's the welfare change? -3, which is much bigger than -1. And also for most of us, 25% of normal consumption is better than dying, all right? So probably for most of us, the utility loss of dying is even bigger than -3. So this says that we're going to underestimate the loss if we simply say it's the loss of utility when you're alive. Now, what what some studies do is they simply add a positive constant to the utility function, B, and then death means consumption goes to some number epsilon, such that utility is 0 because we have B in here. And that means that epsilon is equal to this quantity. But this constrains the loss, and we don't want to do that. You have to do that if you're looking at the welfare gains from health expenditures. But we're not looking at that. We're only looking at death. So we don't need to constrain the loss this way. All right, what are we going to do? Well, let's see. I'll show you that with constant relative risk aversion, we can treat death as a utility loss from a drop in consumption from C to epsilon C, with epsilon much less than 1, but epsilon determined by the VSL. The VSL, I hope many of you are familiar with it, is called the value of a statistical life. We use it a lot in economics, including in environmental economics. It's used for regulatory studies. So in the United States, when they evaluated the gains and losses from requiring cars to have airbags, they knew what the cost would be, about $500 for every car. You multiply that by the number of cars produced every year. That's the cost of airbags. What's the benefit? We save lives. We can estimate how many lives we're going to save. In the United States, 10,000 lives per year was the estimate. Well, now we need a number for the value of each life, and that's called the VSL, the value of a statistical life. How do we get this? It is the marginal rate of substitution between wealth or income or discounted consumption over a lifetime, something like that, and the probability of survival, all right? That's what it is. It's a marginal rate of substitution. And if you simply take lifetime utility as a function of current wealth and the utility from wealth if you die, that's what V is, and a probability of dying, this is what you'll get. This is very easy to derive. This is the VSL, okay? Now, U, the utility when you're alive, and V, the utility when you're dead, are measured in utils. The marginal utilities are measured in utils per dollar, so the VSL is measured in dollars, or euros if you prefer. And it's invariant to affine transformations of U or V. So we can easily go from dollars to euros without any loss of what's happening here. Everything stays the same because that's just an affine transformation, okay? So that's the VSL, very nice. It's invariant to affine transformations. Now in the literature, and there's a huge literature on the VSL, I mean, it's gigantic. People have estimated it in different ways. One way they estimate this is by looking at choices of employment, choices of jobs. How much more money do we have to pay you to take a job where your risk of dying is higher? We look at those choices. And the other thing we can do is surveys. We ask people, what would it take to get you to increase your risk of death? So in the literature, the VSL turns out to be a multiple, an observable multiple, observable from these econometric studies, a multiple of wealth. The VSL is equal to S times W, all right? And these studies find that in the United States, the VSL is roughly 7 times lifetime income or consumption discounted. And that would put the VSL in the United States at around $10 million. And that's the number that the Environmental Protection Agency and the Department of Transportation and the Department of Energy use right now when looking at regulatory policies that can save lives, all right? Roughly $10 million per life saved. You may think that's too high. We'll get to that, but that's what's used. 7 times lifetime consumption. It pins down this parameter S. Okay. Now we can figure out what's utility in the dead state. So U of W is the utility of person with wealth W. V of W is the utility, social utility, if the person dies and their assets are redistributed. We can approximate P as being 0. So let me just go back to this equation. P is the a priori probability of dying before there's any catastrophes. Well, I think for most of you in this audience, I hope for most of you in this audience, the probability that you will die this year is low. I hope it's under 2%, all right? And if that's the case, we can roughly approximate it as 0. We can make P 0, and we'll do that. And if we do that, then this equation becomes simple. Because the VSL is equal to S times W, the equation comes down to this. The utility when dead is equal to the utility when alive minus S times wealth times the marginal utility of wealth. A nice simple expression. It ties down the utility in the dead state. Now we know what it is, all right? And here's the other nice thing. We're going to assume consumption growth, even with potential catastrophes, is IID. And that means that consumption and wealth are proportional to each other. There are many studies that have derived this as a theoretical point. And the constant of proportionality really doesn't matter because the VSL is invariant to affine transformations. So we can work with utility of wealth, a utility of consumption. Either way, we can go back and forth, doesn't matter, all right? So here's what we get. The utility in the dead state, we just plug in the constant relative risk aversion, we get this expression, all right? Looks like constant relative risk aversion, except that W is multiplied by this thing over here. 1 plus S times eta minus 1, all of that to the 1 over 1 minus eta power. So it says that the welfare loss from death is the loss that occurs for a living person if the living person's wealth drops from W to epsilon W, or equivalently, consumption falls from C to epsilon C, with epsilon equal to this thing, which is less than 1, all right? So here it is. This is utility in the dead state. And we can plug this in to the expression for welfare. And now what's total welfare? Well, it's the expectation of the consumption flow times the number of people who are alive, plus the consumption flow, which is smaller now, for the number of people who've died. This is the number of people who are dead. They still get consumption, all right, in welfare terms. So what are we going to do? Let me just make sure, I want to make sure this is clear to everybody. What we've got now is, we haven't said anything about how consumption is growing, the dynamics, but what we've got is an expression that says, look, we know what utility looks like in the dead state. This is the number of dead people. This is consumption in the alive state, and this is the number of people who are living. Nice, simple expression for total welfare. All right, now we need to make this dynamic. We need to describe how consumption and population evolve. So as we said before, consumption, it grows at a rate G, but there are catastrophes that occur. And they're Poisson arrivals with a mean arrival rate lambda C and an impact phi. Each one has an impact phi, and these impacts are IID. So each catastrophe creates an impact independent of the other catastrophes. All right. So here is log consumption. I use a little c, small letter, to represent the logarithm of the big letter. Okay. And at the kth event, consumption is multiplied by this random variable. All right. E to the minus phi k. All right. Now we're going to introduce the cumulant generating function. I'm sorry to do this to you, but this is the one piece of math that we use that you need. It makes life easy. And it's worth learning this because it makes life easy in these models of random growth of consumption, population, and so on, and wealth for that matter. So the cumulant generating function is the log, right, of the expected consumption. It's a function of theta. Theta is a placeholder. So the cumulant generating function of theta, again, it's just a placeholder, is the log of expected consumption to the theta power. And we are using theta to the theta power because we have constant relative reverse conversion. Theta is going to become 1 minus eta soon. That's all it is. All right, this is all it is. It's actually the logarithm of the moment generating function. And it's a very nice compact way to describe uncertainty, to account for uncertainty. And here's what's nice, because log consumption is a Levy process, independent increments. That's what a Levy process is. The cumulant generating function is linear in time. The cumulant generating function for time t is equal to the cumulant generating function for period 1 times t. Very nice. That means that the cumulant generating function is simply the cumulant generating function for one period, time t equals 1, which is just the growth rate times theta, because theta is the placeholder, plus the arrival rate lambda, times the expected value of e to the minus theta phi minus 1, right? Where phi is a representative of the IID phi k's, all right? And by the way, we've said nothing about what kind of probability distribution phi has to have. It can be anything right now. What about population? Same idea. It's an analogous process. Here it is. If there are no catastrophes, the population grows at a rate n, but if there are catastrophes, that reduces the population, all right? And the population falls at an amount, random amount psi k, and these are also IID. So here's the corresponding cumulant generating function. And again, it scales linearly with t. So now we're going to have that the cumulant generating function is just times a placeholder, n times theta, plus lambda d times the expected value of e to the minus theta psi minus 1. And from equation 6, all right, from this equation here, we can write that the expected population, you'll see why I'm doing this in a moment, the expected population is just e to the kappa, the cumulant generating function of one period times t. It's just e to the nt, this is what it would be if there were no catastrophes, minus lambda d with a squiggle times t, lambda d tilde times t. What is this lambda d tilde. It's a death arrival rate, lambda d, but adjusted for the fact that only a fraction psi of the population dies when a death event occurs. Depending on n and lambda d squiggle, the population can grow or shrink in expectation. If disasters are frequent, large lambda d, or cataclysmic, small expected value of e to the minus psi, and n is not too big if n is low enough, then the expected population is going to be declining and the cumulant generating function is negative. All right, but if n is big and disasters are not frequent, the population can grow in expectation. Again, the asterisk means no catastrophes, so n star is just e to the nt, and the cumulant generating function is just n times theta. If you don't avert any catastrophes, if we sit here and do nothing, total welfare is the expected value, again, of n times consumption of those alive, plus the reduced consumption of those who've died. Now, because these are exponential levy processes, consumption and population, they evolve independently, and that's nice because it means that E, the expected value of n times c, or n times c to the 1 minus eta, is just the expected value of n times the expected value of c to the 1 minus eta. We replace theta in the cumulant generating function by 1 minus eta. Here we replace it by the number 1, and that's what the expected value of this product is. And here's the expected value of the number of people who have died times epsilon to the 1 minus eta times their consumption to the 1 minus eta. So now we've got everything that goes in here. And just plug these things into the integral, integrate, rearrange, and this is what we get. What is this? This piece here is the welfare from the guaranteed consumption stream, epsilon c, that you get even after death. It's discounted at a rate delta minus n. This is the additional consumption that you get when you're alive. That's the extra consumption. When you're alive, you get both, all right? And given the risk of death, it's discounted at a higher rate, delta minus the cumulant generating function, which means that it's a rate greater than delta minus n. We discount more highly because of the risk of death. All right. Now, how do we get the willingness to pay? We just set the lambdas equal to 0. If we want WC, the willingness to pay, to avert a consumption catastrophe, we just make lambda c 0, all right? And whoops, I'm sorry. So for example, to get the willingness to pay to avert a consumption catastrophe, we replace the cumulant generating function by this with the asterisk. We make lambda c 0, and then this cumulant generating function is just g times 1 minus eta. But we have to account for the fact that we're giving up a fraction of consumption, WC. That's what the willingness to pay means. It means this is the amount of consumption we're willing to give up. So the welfare is 1 minus this consumption we're giving up times 1 to the 1 minus eta divided by 1 minus eta, plus the welfare of those who are alive, plus the welfare of those who died. And all we do to get WC is we equate this V sub C to V when we don't have lambda C equal to 0. That's it. And here are the results. So the WTPs, the willingness to pay, they are given by these expressions. These look messy. They look like nasty things. Well, these are just cumulant generating functions. Right now they're general because we haven't said anything about the probability distributions for what happens when there's a death event or a consumption event. We haven't said anything about that. So in order to go any further, we need to specify something about the probability distributions for psi and phi. By the way, we can show that the willingness to pay to avert both consumption and death catastrophes is less than the sum of each willingness to pay minus the product. This is actually a stronger result. That's what is in our 2015 American Economic Review paper. All right. So we need to say something about these probability distributions if we want to go further. And we're assuming that they are exponentially distributed. And this is very nice because it means that they're characterized by a single parameter, beta C for the consumption catastrophe and beta D for the death catastrophe. It says that for a consumption catastrophe, the probability distribution, all right, for phi is just beta C times e to the minus beta Cx, and likewise for a death catastrophe. And now the cumulant generating functions become very simple. This is what they look like. They're very, very simple now. They simplify, okay? And now we can define a couple of things. Rho is, we're going to define this to be delta minus n plus g times eta minus 1. What is that? That's just the discount rate on consumption, given the possibility of catastrophes. And we're going to define lambda C prime and lambda D prime as the risk-adjusted and impact-adjusted arrival rates. So look down here at lambda D prime. Lambda D is the actual arrival rate of a death catastrophe. The bigger is beta D, the less severe the catastrophe is, all right? And that makes lambda D divided by beta D plus 1 smaller. So we're adjusting for the severity of a death catastrophe. Here, we're adjusting for the severity of a consumption catastrophe, and we're also adjusting for risk aversion. If we increase eta, it makes lambda C prime bigger, okay? So these are just risk-adjusted and impact-adjusted arrival rates. They allow us to see things a little more clearly. And if we plug these in to the expressions for the cumulant generating, plug in the cumulant generating functions, and plug in these things, rho and lambda C prime and so on, to the expressions for the willingness to pay, this is what we get. And again, this may look, terrifying, I don't know, but these are just parameters, all right? These are simply parameters. And by the way, epsilon here, remember, is given by the VSL. It's just S times eta minus 1 plus 1, epsilon to the 1 minus eta. It's very simple. So all of this becomes actually quite simple. How do we calibrate this? We need numbers for lambda C and lambda D, the arrival rates of these catastrophes, beta C and beta D, the impact parameters for these catastrophes, and S, the VSL. We also need to know eta, the coefficient of risk aversion, delta, the rate of pure time preference, N, the normal growth rate of population, and G, the normal growth rate, real growth of per capita consumption. We need those numbers. We need these numbers, 9 numbers, to calibrate the model. How do we do it? Let's start out with the catastrophes. We're going to start out with pandemics. Now, we wrote this paper before COVID. We used data prior to COVID. So based on pre-COVID data, we took all the pandemics we could find. What we got was a lambda D of 2%, means every year there's a 2% probability, 2% chance of a serious pandemic occurring, and beta D equal 24, which means if a pandemic does occur, the expected population mortality rate would be 4%, which is what it was for the US during the Spanish flu. Of course, it could be higher or lower. This is a random variable. All right. So we also look at a higher risk scenario, the same impact parameter, probability distribution, but we're going to double the arrival rate. Now, why do we do this? Because 2 years ago, 3 years ago, and 4 years ago, before COVID, the Centers for Disease Control published studies, and they said very clearly, you can see the quotes in our paper, that there's going to be a pandemic, bad pandemic, Spanish flu or worse, and it's going to happen, and it's going to happen soon, and it's going to be a virus that's going to be animal to human transmitted, and it's going to be worse than Spanish flu because people are traveling all over the world. That's what the CDC said. What did the World Health Organization say? Same thing. Everybody said 2 years ago, 3 years ago, 4 years ago, get ready. We are going to have a pandemic, and it's going to be bad, and it's going to happen soon. So the high risk scenario, I double this number for the arrival rate, says there's a 4% chance. You may think that's too optimistic. That's what we did here. What about, what about the recession, the economic parameters? Well, we're going to use the Barrow-Rousseau data for world and US GDP contractions of 10% or more. We adjust them for any contractions, and that gives us, if we use world contractions, lambda C of 8% arrival every year, a beta C of 7, it says there'll be a contraction of 13 years on average size 12%. We use, if we do it for the US and we add the 2008 recession, which Barrow-Rousseau didn't have data for, the estimated contraction size was 10%. It gives us a lambda C of 0.29, beta C of bigger beta C. It says there's a contraction every 3.5 years with an average size of 5%, okay? This is higher risk, actually. So we have two settings, the low risk, P1, R1, high risk, P2, R2. All right, what do we get? These are the characteristics of the shocks, and this is the loss, probability of at least one shock over a horizon of 20 years with a loss greater than or equal to L. And this is the expected total loss on the right over some horizon T for these different potential catastrophes. Now you may look at this and say, wait a minute, this death catastrophe doesn't look so bad, right? It's way below the consumption catastrophe. This is the death catastrophe. But remember, here the loss is people who die. Here the loss is consumption. Dying is much worse than losing consumption. So this does not mean that the welfare loss from death is less than the welfare loss of a loss of consumption. Okay. Now these WTPs depend also on eta, delta, G, and N, and the VSL parameter. We're going to use values for eta and delta broadly consistent with the macrofinance and consumption disaster literatures. So my own work with Neng Wang of Columbia University, we simply took a general equilibrium model and we backed out the value of eta and delta given stock market data to characterize consumption catastrophes. And we got that eta was about 3 and delta was about 5% rate of time preference. Barrow, in his 2009 AER study, he got eta of about 3.5 or 4 in that range, and delta of about 0.05. So we're going to set delta equal to 0.05. We're going to make eta 3, but we'll also look at other values of eta. US data puts G at 2.02 and N at 0.01 historically. That's fine. We'll use those numbers. S, as I said before, is typically 7. That's the mid-range of the estimates of the VSL. That means epsilon to the 1 minus eta is 7 eta minus 6. And we're going to calculate each willingness to pay, WC, WD, and the willingness to pay to avert both. But we're also going to calculate these things, WC prime, WD prime. What is that? WC prime is the willingness to pay to avert a consumption catastrophe, but ignoring the existence of a potential death catastrophe, ignoring that. And likewise, WD prime is the willingness to pay to avoid a death catastrophe, but ignoring the possibility of consumption catastrophe. All right, we'll see that's important. And we'll look at these two sets of calibrations, low risk, high risk. I'm going to focus mostly on the low risk because I don't have a lot of time. Here's the low risk pair. This is the consumption catastrophe parameters. These are the death catastrophe, pandemic parameters, which are probably, this is probably overly optimistic. The CDC and the World Health Organization would say, come on, that's too optimistic, but let's use it. And what are we going to get? This is pretty amazing. Look what we get on the left. This is for the WTP, for each WTP versus the coefficient of risk aversion, holding S equal to 7. All right. So what do we get? If 8 is 3, we're getting a willingness to pay to avert a death catastrophe of about 10%. We would give up about 10% of consumption now and all through the future to avert a pandemic. That's what this says. And what about averting a major recession? We would give up about 23, 24% of consumption. That's amazing. That's a lot. And by the way, that's what the literature on consumption catastrophes says. The same thing, that economic fluctuations, economic uncertainty is very, very costly in welfare terms. Something else you can see here, and that is, this is the willingness to pay to give up both. It's less than the sum of these two, but it's pretty substantial, almost 30%. And what is this dotted line here? This is the willingness to pay to give up a consumption catastrophe, ignoring the possibility of a pandemic. It's lower. The existence of a pandemic, threat of pandemics, raises the value of getting rid of consumption risk. And consumption risk raises the value, here it is, from here to here, of getting rid of a pandemic risk. And as you increase the coefficient of risk aversion, the willingness to pay to avert a death catastrophe, a pandemic, doesn't change a whole lot. Willingness to pay to avert a consumption catastrophe grows, and it grows a lot as eta gets big. Now, some people would say, including me, I would say this, that an S of 7 is too big, that a value of a statistical life of $10 million, which is what S of 7 gives you, for the United States is too big. Why would I say that? Because if you take the population of the United States, 330 million, and multiply it by 10 million per person, you get $3,300 trillion. Well, that's far, far bigger than the present value of all GDP, allowing for GDP growth over the next 40 years. So I think that's too big a number. So what happens is we change it. If we lower S, as you'd expect, the willingness to pay to avert a death catastrophe goes down. But you know what? Even if we cut S in half, cut it, make it 3, we're still getting a willingness to pay of 4 or 5%, which is a huge number. All right, these are the same curves for the higher risk sets of parameters. I'm not going to spend time on this. And these are the willingness to pay when you ignore, it's the ratio of the willingness to pay when you ignore the other catastrophe to the willingness to pay when you don't ignore it. And you can see the other catastrophe makes a big deal, makes a big difference. All right, what are the conclusions here? And then we'll open this up for questions and discussion. First of all, high values of WC and WC prime, these support earlier studies showing that there are large welfare costs of macro risk. And these costs are partly due to the threat of other catastrophes, and here it's pandemics. And economic risk raises the welfare cost of pandemic risk. WD, a third lower if we can eliminate economic fluctuations. Even for low risk calibration, the willingness to pay to avoid pandemics is around 10% of consumption, $2 trillion per year for the US. And cutting S to 3 cuts this in half, all right? So, even if you use 3 or even 2, you're going to get a willingness to pay to avert pandemics of 4%, 9% of consumption. Is that unrealistic? Well, remember, this is a reservation price. The actual cost of averting pandemics is probably much lower, but it says we should spend far more than we do on pandemics, much, much more. Right now, we're spending almost nothing in the United States. We're spending almost nothing worldwide. The World Health Organization has a tiny budget, likewise the CDC. All right, let me stop here. And I assume, Sergio, you're going to take over, and I'm going to see a new screen.
Yes. Perusa, now we have a list of questions. So we start with Professor Borghesi from University of Siena and the European University Institute.
Okay.
So I leave him the floor for the question.
Yeah, thank you, Sergio. Thank you, Professor Pindyck. Extremely interesting and inspiring presentation. I'd like to take the opportunity to thank Sergio for organizing it and the Fondazione and the University of Brescia. It's a great event, and I think on behalf of the Italian environmental economists, we're all very thankful to Sergio and to you, Professor, for your participation. I have a couple of questions. The first one is, what happens if the catastrophic events are dependent, are not independent? So, you know, there is some evidence that the current pandemic might be related or even caused by the destruction of the environmental habitat. So would your results change accordingly? And secondly, you clearly express the history of the Spanish flu with 4 or 5% of people dying in the US, but no fall in consumption. We probably expect a difference now with, unfortunately, a high number of deaths, but also a real collapse, or the danger of a real collapse in consumption. So what might be, in your opinion, the reason for the difference between these two events? Thank you.
Yes, so let me take your first question, and that is, you're absolutely right. We treat these events as independent in this paper. We don't have to. We could make them interdependent, and you're quite right. With COVID, COVID not only has been killing people, but it's been damaging the world economy. So there's no question that it's had an economic impact. We can do that, and if you go back to our 2015 American Economic Review paper, we do it, and we show how you can modify the analysis to allow for interdependent events. For example, a nuclear terrorism could be related to bioterrorism, for example. So we can do it. It makes the math more complicated. It makes everything more complicated. So for this paper, we chose not to do it, but we could. It just makes things a little trickier. What it would do is it would increase the value, the willingness to pay to avert a recession. I'm sorry, to avert a pandemic. What it would do is whatever number we get here to avert a pandemic, it would go up if we allowed for the fact that pandemics also have an economic impact. Now, in terms of what happened in the Spanish flu, I don't know, but for some reason in the United States, GDP didn't change much. It didn't affect GDP very much. And you may say that's surprising, but somehow that's what happened. Maybe it's a measurement issue. I don't know. Because certainly COVID is affecting the economies of almost every country.
Thanks a lot.
A question before leaving the floor to Professor Peterkort. So in the other paper, you think also there is a link between disaster in the two directions. So pandemic caused also by an increase of growth rate or not. So it's a combination of pandemic on the effect on pandemic effect on consumption, or both of the two effects.
So the way we could make, the way we did it in the American Economic Review paper is what we did is we said that the arrival, in this case, let's say, the arrival of a consumption catastrophe could make the arrival of a, either make the arrival of a pandemic more likely, or vice versa, or it could also have a consumption effect. So the easiest way to do this is to say, look, we don't change the growth rates, N or G. What we would do is say, look, if a pandemic occurs, there'll be a drop in the population, some fraction will die, and there will be a sudden drop in consumption. We allow for a drop in consumption, even though it's not a consumption catastrophe. That's the easiest way to do that, and that's how we would modify this to include the interaction.
Okay, thank you. Okay, now I leave the floor to Professor Peter Kort.
I don't see anybody.
Very good.
Professor Peter Kort for University of Tilburg.
Thank you, Sergio, for organizing this. I know that we prefer all to be in Brescia right now, as Professor Pindyck already told, but well, this is kind of a next best thing. Professor Pindyck, I'm impressed by your paper, by your presentation, and thank you for giving such a clear presentation. I was thinking about the kind of the practical meaning of willingness to pay that you calculate, and to connect it with the current lockdowns that we experience in the different countries. Implementing a lockdown, in fact, implies that there is a reduction in health costs at the expense of economic growth. So how can I see your willingness to pay in this light? Is it equal to the maximum reduction in GDP that a lockdown can cause when implementing optimally, or can there be a connection made in that sense?
Right. Let me clarify what a willingness to pay means. Willingness to pay is a reservation price. In this case, the reservation price for society. It's the most society would give up in terms of GDP or consumption in order to prevent something. In this case, prevent a pandemic. All right. It doesn't say that's what they have to give up. It's just like the reservation price you might have for a cup of coffee. So for me, in the morning, the first cup of coffee, my reservation price is really high. I'd be willing to pay $30, but I don't have to. I can pay $1 or $2, all right? But the most I'm willing to pay is $20, $30. That's what we mean by a reservation price. What this says is that the most society would be or should be willing to pay is, let's say, 5% of consumption, or 5% of GDP, all right, which is $1 trillion per year for the US. It doesn't mean that's what they have to pay. If it's done optimally, if COVID, for example, is managed optimally, it could be that the sacrifice of GDP would be much less than 5%, maybe 1%, 2%, I don't know. But that's what we mean by willingness to pay. It's the most we'd be willing to pay. Clear?
Yep.
Professor Kort, if he has other questions, otherwise, okay, I can move to others. Here there is another one that is asking if it is possible to measure the welfare loss under concomitant disaster, e.g., for example, a hurricane during a pandemic lockdown. So it's I have to say that I've seen a model this morning with this combination of. Is it possible?
Sure. Yeah, easily. So again, in our 2015 American Economic Review paper, we allow for any number of catastrophes, potential catastrophes. And one of the first slides I showed you was a result from that paper for 7 different catastrophes. Here, we wanted to keep things relatively simple because the focus here is how do we handle death? How do we think about the welfare costs of death? And so we kept it simple by having only 2 types of catastrophes. But we could have others. We could add more. It just means that this gets a little more complicated, but it's easy to do. So here we kept it simple, but we could easily add one more type of catastrophe.
There is also Professor Menoncin that is not able to, from the University of Brescia, Francesco Menoncin. Okay, perfect.
Okay, the dead people never truly die. They instead. So they do die. So I know this is hard to accept. So you know, why would there be any welfare when you're dead? So first of all, remember, we're looking at social welfare. But even for you, if you make bequests, if you say, look, when I die, you know, my wealth goes to my children, let's say, or my spouse and children, well, then they're going to consume, and that gives you utility. That we can call it a utility when you're dead. It's a utility in the dead state. It's a social welfare in the dead state, and it's real. You're still dead. I'm sorry to say. You're not going to be able to go out and buy a cappuccino when you're dead. You know, that's the way it is. To my knowledge, I've never been dead, so I don't know for sure, but that's my understanding. Is you can't do everything. But on the other hand, there's still a social welfare. So that's the idea here. And everything that's been done with the value of life, the value of a statistical life, involves a welfare when in the dead state. Okay, now the next question, the consumption C, as you define it as a jump process, never becomes negative. So why are you worried about C becoming zero? Well, because C could get arbitrarily close to zero. That's the problem. So even though it can't reach zero, it can get arbitrarily close to zero, and then utility becomes arbitrarily close to negative infinity. So that's why we worry about that. And then number 3, the agents are not optimizing. No, they are actually. What we're doing here to get a willingness to pay is this is what you're willing to sacrifice. This is optimal. This is the best you can do. This is your willingness to pay. We're not accounting for what's required to pay. We're simply saying this is what you're willing to pay. And this is true with jump processes or any other. And then lastly, number 4, willingness to pay is the demand side of an insurance market. What about the supply side? How will you model this in your framework? So in the 2015 American Economic Review paper, we look at estimates of what it would take to eliminate or reduce the likelihood of certain catastrophes. We get that from a variety of sources. And if you look at then, if you go back to that paper, you'll see examples. We didn't do it here. We didn't bother with it here. So if you ask me today, what would it take to eliminate the possibility of a pandemic? I don't know the answer. We didn't try to come up with that here. We do have some numbers in the earlier paper. I don't remember what they are, but we haven't tried to update that. But that's how you would do it. You'd look for numbers. What would it take? How could we either lower the likelihood, lower the value of lambda d, or make it zero? What would it take to do that? And you know, there are studies out there. We could look at them. We don't do those studies ourselves. We look at what other people do or have done. Okay, I hope I answered those 4 questions.
Okay, thank you. Now, the next is Professor Fulvio Fontine here from the University of Padua.
Hello.
Hello.
Thank you. The model you presented here deals with average figures or a representative consumer with a given, assuming different degree of aversion, risk aversion, and possible figures. I would like to know if you have any idea about what could happen to the willingness to pay and to the results you derive when you take into account distributional effect of the different catastrophes.
Yeah. Right. So 2 things. You're absolutely right. We ignore the fact that people of different ages have a different value of staying alive. If you're 99 years old, what is your VSL? What's the value to you of avoiding death? Well, you're probably going to die pretty soon. I mean, I guess in Italy everybody lives longer, but here in the United States, you know, you're going to die soon. So the value is not that high. If you're 20 years old, very different. We ignore all of that. I guess we're assuming everybody's 40 years old, let's say. We ignore wealth differences. You know, how much wealth do you have that's possible to give up? But here's something how it would change the results. COVID, unlike the Spanish flu, So the Spanish flu, as you may know, disproportionately killed young people, children and young people, not old people. COVID disproportionately affects older people, me. I don't know how old you are, but older people, all right? And if you took that into account, the VSL number, the number 7 we're using for S, would be lower. Why? Because older people, 70-year-olds, 80-year-olds, whatever, they don't have that long to live. And therefore, the value of life is lower for them. There's a whole literature on the value of a life year, of each additional year of life. And that takes into account the probability that you'll die anyway of something. And we don't deal with that. That makes matters very complicated. We don't deal with it at all. But there's a lot of papers out there, a lot of big literature that does study that. I hope that got at your question. I'm not sure if I answered it.
Thank you. Probably that means that the willingness to pay of COVID will be reduced to take into account the different impact on the population, on the cohort of the populations. But thanks, yes.
Yeah. Here it is. Let me just read this. How sensitive are the results to the assumption that the catastrophes are Poisson or rivals? With, say, climate, there's some element of predictability. Would you say that leads us to pay more if we saw that a catastrophe was more likely in the near future? Yeah, absolutely. I mean, you could argue that climate is different from a pandemic or nuclear terrorism or even an earthquake, in that that's a sudden event that happens all of a sudden. Climate grows gradually. And sure, I mean, you'd have to model climate a little differently. We didn't when we did our 2015 American Economic Review paper. We treated climate in the same way that we treated, pandemics and nuclear terrorism. But if it's something that you think is very likely, then of course that's going to raise the willingness to pay to avert it. Here I see it. It says, I provide a framework for the consumption side. Should we consider the permanent or temporary loss in productivity as redundant, or rather to be summed up in this framework? In other words, what is the correct way to also account for the loss from the supply perspective? So we don't really have a model of the economy here. If you go back to the paper I wrote published in 2013 with Neng Wang, we have literally a general equilibrium model of the economy with adjustment costs, investment, productivity, everything. And there we look at how a consumption disaster could work through a drop in productivity to affect the economy. We don't do that here. And we don't do it in the 2015 AER paper either. Here, there's no economy, really. There's just consumption. I mean, people are consuming. And where the consumption comes from, we don't really care about. We don't really talk about. So there is no real productivity. There's just, if there were no catastrophes, no death catastrophes, no consumption catastrophes, the population would grow at a 1% a year or 2% a year. I forgot what number we used. And consumption, per capita consumption, would grow at 2% a year, and that's it. Why it grows that fast? We don't deal with that in this paper. So you have to expand the model in order to deal with that.
Okay, perfect. So there is another one,
I see it. Does it make a difference between catastrophes that can be avoided or mitigated and those that are natural? Quakes, hurricanes. What about different strategies to mitigate a catastrophe, such as a policy response? So first of all, let me clarify something. Let's take hurricanes and earthquakes. Take hurricanes. And you may say, look, hurricanes are natural. You can't prevent them, okay? And that's quite right. But what you can do is prevent the damage, which is just like preventing the hurricane. So for example, in the United States, hurricanes are going to cause homes and buildings that are near the ocean to go into the ocean, to get washed away. Well, that says we shouldn't be building homes right on the ocean. That's not a good idea. And in the United States, we even subsidize those homes because the government provides insurance. So it says that what you can do is you can't stop the hurricane from happening, but what you can do is stop the hurricane from having an impact, which is like just as good as stopping it from happening. You'll have a hurricane, but it won't do any damage. So that's how you think about that. Same thing with earthquakes. You know, in Chile, I was recently in Santiago, and you know, in Chile, they have earthquakes and they have very strict building codes so that when an earthquake occurs, the buildings don't collapse. Well, that's the same thing. You're not going to stop the earthquake from happening, but you're going to reduce or eliminate the negative impact. See, that's how you treat that.
Now there is another question, I think, from the Professor Maria Laura Parisi from the University of Brescia.
Yeah. Okay. Now, can you hear me?
Thank you. Yes.
Thank you, Professor Pindyck. I'm really happy to listen to your seminar. My question is, the reservation price, the willingness to pay, can be different for different countries. What happens if, for example, a country does not care at all about protecting from the events of catastrophes such as climate change impact that might affect all other countries and all other countries' probability of a catastrophe event, and so they might have an effect on the willingness to pay at that point?
You are absolutely correct, and here's how I would answer it. First of all, the numbers I used in this presentation were based on the United States, because that's where I live. But if you look at the UK, I don't know whether that's not Europe anymore, it used to be part of Europe. But if you look at the UK, their willingness to pay, their VSL studies, the value of a life is much lower. And the National Health Service in the UK, they use a VSL number, which is much lower than what it is for the United States. In the United States, I think I said it was around $10 million, which maybe is too high. In the UK, it's only about $1 million. So if that is your value of a life, you're going to have a much lower willingness to pay to prevent a pandemic, no question. And there will be big differences across countries, no question. And so, you know, and by the way, much of my work right now, literally this, you know, now the work I'm doing these days is, how do you think about this VSL? I mean, what's the right way to think about it? If the $10 million number is too high for the United States, what's the right number? And how do we get that number? And so that's really a fundamental question. So you're absolutely right. It's going to vary across countries.
Okay, thank you very much.
You're welcome.
Thank you very much. Thank you very much. Now we are perfectly in line with our timetable, so we can finish here. I would like to thank you very much to Professor Pindyck. It was a seminar very, very interesting. So we hope to see soon, and so we can also keep in touch for other seminars in the future, other things. You know that I asked to you for our association, Environmental Resource Economists. Thank you very much, Robert.
Thank you, Sergio, for organizing this. And I want to remind you that even though I did this seminar, you still have to take me to dinner when I come to Brescia, okay?
Yeah. Yes, yeah.
And I haven't been in Padua for a long, long time, but they have nice restaurants too. So there's a lot of good food that we have to go and experience. I have a very high reservation price for experiencing that food. But thank you very much for organizing this.
No, thank you too. Thank you for having accepted our invitation. Thank you. Thank you for all the participants that are very, very, very high number. We are 150. That is a very, very good number for your seminar. Thank you, Robert.
Right. Thank you, everyone. Bye-bye.
Thank you. Bye-bye.